Hello, I'm Neville. I'm a security researcher. I'm also co-founder of DDoB, and I'm also a computer science academic. In today's talk, I'll be talking about how to use decompilation to find security vulnerabilities. So let me introduce DDoB. DDoB is a security company. These are some of the projects that we helped secure over the last few years. We've been around since at least 2001 and even before that. We mostly offer security audits, monitoring, and also products and solutions that make use of static program analysis and decompilation. Now, my co-founder, Yanis Maragdagis, he popularized a form of static program analysis called declarative static program analysis. It is a very interesting method by which you can model all possible executions of a program. And as security researchers, we are interested in some particular executions of the program that exhibit bugs, that exhibit security issues. And in declarative program analysis, what we essentially do is we turn a program into a relational format, into a database, so to speak. So here's a program on the left-hand side. It's in an IR, which is similar to YUL. And the relations that we extract from the program are things such as, for instance, this variable is assigned to this other variable, or this instruction is the next instruction after this one. So it's like 2 or 3 column tables, so to speak. And then we run queries on these, this relational database, so to speak. But we run these queries using a special language called datalog. And the strength of datalog is that it allows for highly recursive queries. Now, it just so happens that most program analysis algorithms are also highly recursive. So this language is a match made in heaven for us. So here's an example of a very, very simple program written in datalog. It's these 7 lines on the left. And this program finds, if there's information about programs such as, for instance, flows and induction variable, it finds actually the number of iterations by which this loop is bound by. And then in this case, it finds that this loop in this program is bound by variable n times. Okay? So we've run a lot of algorithms. We've implemented a lot of algorithms using this approach, and we've ran them 24/7 on many machines trying to find vulnerabilities in smart contracts in the wild. We found a few things. So for instance, we found the CVE in Uniswap. We found 2 Solidity compiler bugs that have since been fixed. And we've also found a very, very serious vulnerability on a bridge called multichain. In this vulnerability, one could have effectively stolen all the liquidity in this bridge. It was over $1 billion of liquidity. We reported these, and hopefully, things didn't go that bad. So I'm going to be talking a little bit more about decompilation and how it relates to finding security vulnerabilities. But in order for you to understand it, the first thing I need to discuss is how smart contracts in Solidity are compiled and how they turn into bytecode and the phases that they go through. So this is a smart contract. It contains 1 constructor, 1 function, and 1 storage variable. Now, when the Solidity compiler compiles this code, it will generate 2 kinds of code. It will generate initialization bytecode, and this bytecode only contains the constructor and some other things. And this constructor is only going to be executed once using the create or create2 opcode. And then there's the runtime bytecode, which is going to have the rest of the program. Okay, so the runtime bytecode does not have the constructor code. Remember this for later. Now let's just look at the runtime bytecode of the same program. Okay, this is how it looks like. It's called bytecode because every single byte is a different instruction. 90% of the time that's true. So for instance, if you look at the very first instruction, that's 60 in hexadecimal. That's the first byte. 60 is push 1. Okay? Now, the problem is that once you have compiled the code to bytecode, you have lost a lot of things. So you can disassemble the bytecode very easily by applying certain rules. And this is the disassembled version of that program that I just showed you. However, the disassembled version has lost a lot of things. It has lost variables. It has lost types, all names, functions, expressions, control flow, and many other things. Okay? So in fact, this code is not very useful to inspect. Like, there's not much you can do with it. You can execute it, I guess, and there are some approaches, such as, for instance, fuzzing, which are mostly executing code many number of times per second. So this kind of works for that, but not for static program analysis. In the case of static program analysis, we need to recover a lot of the structure in order to start running our algorithms. Okay, so the very first thing that we need to do, the very first step, is to split this program up into what we call in the static analysis industry, so to speak, basic blocks. Okay, and how do we find basic blocks? So the very first instruction is the start of a basic block. Now, a basic block is a sequence of instructions, a maximal sequence of instructions, such that if you execute the first instruction, you're going to go through each subsequent instruction. Okay? And there are different rules by which we are able to decompose this into basic blocks. So this is how they would look like on the right-hand side. They would be like 10 instructions, for instance, that you can think of as, if you enter one of them, you will go through all of them. Okay. Now, once we have these basic blocks, we then run a lot of algorithms, such as data flow analysis algorithms, in order to find what the jump targets are of these basic blocks. And we start to recover structure slowly and slowly. And this is an intermediate level output of our decompiler. This is called tree address code. And even though it looks difficult to understand, at this particular level, it enables a lot of analysis, such as static program analysis. You can do formal verification on this. You can do model checking and many other fancy things. Even fuzzing these days relies on a tree address code representation, because fuzzing has become more complex over the years. So at this point, we have recovered variables. Note that in the actual representation of bytecode, there are no variables, right? So the Ethereum virtual machine is a stack machine. We have recovered functions. We have even recovered private functions. And we have recovered control flow. Now, if you note, it might be difficult to see, but we know at this level, for each basic block, what's the next basic block. So we know that this code, it starts over here, and then from here you can go to there or there, for instance, based on a condition. You don't know that when you're disassembling code. Okay, so here's another representation that our decompiler offers. So if you want to play with our decompiler, just go to Google and search for Ethereum decompiler or DDoB decompiler. This is a higher level representation of the program than what I've just showed you in the previous slide. And in this level of representation is very good for inspecting code, meaning that if someone has deployed a smart contract without any source, you can use a decompiler and you can understand what they did. Some people do it to reverse engineer, like their competitor strategies. Some people do it because, they're doing forensics, on-chain forensics, for instance. We do it also for security analysis. Okay, so at this level of representation, you get even more. You get complex expressions, you get function names, and there's less low-level code at this level. Okay, so now that we have a decompiler, how do you use the decompiler to find security vulnerabilities. Now, in order to get that, to understand that a little bit more, you need to understand that static program analysis, again, it's a tool, it's a technique that enables you to model all possible executions of the program without running the program. However, that is, rather a theoretical description, because actually it is impossible to do it generally, to do it fully precisely, so to speak, because of something called the halting problem. But we can abstract the execution of the program. We don't need to have very, very precise execution of the program. But when you abstract the execution, it leads to a lot of false positives. In practice, we also allow false negatives, meaning that not only do we accept that static program analysis algorithms will give us vulnerabilities that don't exist, in reality, we also accept that they will not give us vulnerabilities that are there. Okay, so that is rare, but it happens in practice as well. So in our case, what we do is we have a system in place called symbolic analysis. Again, you can Google it, and there's publications about this. So in symbolic analysis, we prove using theorem proving techniques that certain executions can indeed happen because there's a proof that shows us that, so it's possible according to conditions in the program. And most security analyses have actually the form of, some sensitive operation can be reached by an unprivileged caller. Let me give you an example of one of these vulnerabilities. So here's one. This is something called reachable swap. If you guys remember the DeFi summer of 2020, there used to be a lot of yield farming protocols out there. And these yield farming protocols, they relied on someone, manually or like automatically to call a harvest function. So this function can actually be called by anyone, right? However, this function does a swap, a rather large swap of the protocol's funds on an LP that can be predicted, right? So what an attacker can do is that they can find the LP, do a giant swap using a flash loan, for instance, then call harvest, and then extract the money back. So these kind of vulnerabilities, reachable swap, used to be common. We had found one on Harvest Finance, for instance. We got a big bounty. But nowadays, things have become a little bit more complex. One other thing that we can use this security analysis on is to ensure that Ethereum upgrades are not going to brick certain important smart contracts on chain. So since the analyses are extremely fast, we can run them on all smart contracts ever deployed, and we can provide some assurance to the Ethereum team, the Ethereum Foundation in this case, that their EVM upgrades are not going to break contracts. So we've done a lot of studies with the Ethereum Foundation. The last one we did was a few months ago. And in these studies, what we usually do is we create two semantics of the Ethereum virtual machine. We see, does the contract work in this semantics, but doesn't work in this one, in the updated one? Then we need to look into it further. All right. We've also identified, as I said before, vulnerabilities in the Solidity compiler. Now, this is something, obviously, that decompilation is very, very useful because, we were noticing that we were decompiling smart contracts, and we were finding that 90% of their code was basically dead, meaning that there was no way you could possibly reach that code. And as I mentioned before, code that is in the constructor doesn't need to be in the runtime bytecode. It just so happens that Solidity compiler had a bug, and any library that you used in the constructor in many different versions of Solidity, I think from 0.7, also 0.8 had this problem. It was including code that basically it didn't need to be there. So in practice, on average, 30% of the code ever deployed on Ethereum, within certain time range, it was effectively dead. It was there, but people paid the gas to deploy it, but it didn't need to be there. So then the Solidity team fixed that. Now here's something that we found with the help of our friends at Venn Network and also SEAL, Security Alliance. This is something that we worked on just last week, so you guys are the first to hear about it in a presentation. This is a very, very insidious vulnerability. In fact, there were many, many protocols that had this, including, for instance, EtherFi, Origin Protocol, Berachain, Pendle, and others. And in this particular insidious vulnerability, what the attacker did is that they listened to deployments of proxies. Proxies being smart contracts that don't have logic, they store the state, but they delegate to an implementation. This way you can upgrade your implementation. So he was seeing that there were these proxies deployed on chain, and the initialization function was not executed yet. So he was executing the initialization function and setting their clandestine proxy, so it's yet another proxy, as an implementation to the original proxy. Now, this clandestine proxy, in order to evade detection, it was routing to the legitimate implementation. So the protocols were operating normally, but this clandestine proxy was basically a backdoor to the protocol. Like, it was owned by the attacker, it could do anything that the attacker wanted. Like, if the attacker wanted to drain the protocol, he could do it. They were basically waiting until these protocols or these smart contracts became big enough for them to just, attack. So it's a game theory sort of situation. It had very, very insidious features. I'll just show you a few here. So the attacker obviously invested a lot of time creating this malicious proxy. So for instance, it had a feature by which if someone tried to upgrade the proxy in order to recover from this in any possible way, at the end of the execution of any call which goes through this proxy, it would silently make itself the implementation of the proxy again. So there was no way to get rid of it. Okay? It would also silently update the administrator of the protocol and all of that. The other thing it did is that it exploited a vulnerability in Etherscan, and Etherscan was not showing the clandestine proxy as the implementation, but it was showing the legitimate one. And that's because the attacker figured out that if they updated a certain storage slot, it would fool Etherscan into thinking this. The attacker also made this proxy to be very, very highly flexible. So it could route, for instance, to different implementations based on, if the attacker, for instance, figured out that a particular smart contract that has been attacked is worth doing something custom for, he could do it. Now, in the case of Pendle, for instance, he actually added a module to this, which basically prevented withdrawals larger than 90% of the balance in order to make the recovery process more and more difficult, okay, for the team. Now, the interesting thing is that this happened only last week, all right? So we have successfully mitigated most of the vulnerability that these protocols had, due to this issue. I believe there was over 10 million just, on many protocols that they could have just stolen. And the thing is that each protocol, because it had different logic, it had its own story by which you could recover, right? So each protocol needed customized way to recover. But there were ways in which we could recover this because there were certain admin functions that were still exposed, so the attacker didn't block every single admin function. So yeah, or completely patch the dependency, but this smart contract, which is vulnerable, is still there, but now becomes deprecated. So yeah. Now, what's the reason why I brought this up is that the attacker had many different variants of this malicious proxy. And we wanted to find all of them, right, in order to find all the protocols that had this issue. So what we did is we used our decompiler. We figured that all of these proxies had some common logic between them. We looked for that logic on all the smart contracts deployed on chain, and we found all the malicious proxies that were deployed by this attacker. And then then once you do that, you can figure out what protocols have been attacked by this proxy. So that was a very, very cool story. Again, it's like something that we participated in, but also Venn Network actually found the issue to begin with on their own smart contracts, and Security Alliance coordinated the war room with the many different protocols. Okay, so in conclusion, so DDoB, as our team, we find vulnerabilities using very unique approaches, using static program analysis. And because of that, we can find some vulnerabilities that other firms might not find, because we look at code at a very different angle, so to speak. So we look at code at a very low level, and you get a different perspective on the code. We do decompilation, static analysis, and also blockchain indexing these days. We've been successfully prevented billions in stolen funds across many different activities. So yeah, that's it. Thank you very much.